So while we spent 12.2 adding and subtracting and multiplying vectors by scalar, it may have occurred to some of you to wonder, can we multiply vectors by each other? And the answer is yes, and it is occasionally interesting to do so. One way that we can multiply vectors by each other is what's called the dot product. And the dot product is defined this way. So if I have two vectors, a1, a2, a3, and b1, b2, b3, the dot product a dot b, you literally write a dot, is equal to a1 times b1 plus a2 times b2 plus a3 times b3. All you do is you grab the first two elements and you multiply them together, and then you grab the second two elements and multiply them together, and so on and so forth, and add them all up. One notable difference here is that this is a scalar. It takes two vectors enter, one scalar leaves. They lose their vector nature. So the dot product, although it tells us some things, also you lose a little information. You go from being a vector to being a regular old scalar. Let's just try one of these real quick. We'll take the vectors -7, 2, 3, and we'll do the dot product with the vectors 1, 4, 1, and see what we get. So we take our -7 and our 1 and we multiply them together to get -7, plus 2 times 4 is 8, plus 3 times 1 is 3. So this happens to come out to equal 4. Hooray, the dot product of those numbers is 4. Well, what the heck does that mean? Well, we'll get to the interpretation of it in a second. There are a couple interesting properties of the dot product. One, well, we can ask ourselves this question. If I have some vector A, what is A dotted with itself? Well, if I dot A with itself, I get, let's see, a1 squared, because you'd match up the first element twice, plus a2 squared plus a3 squared, and you might recognize this as just being the magnitude of the vector A squared. So if you dot a vector with itself, you get its magnitude squared, which we will use. Now this does have a geometric interpretation. Let's say we have two vectors, A and B. Here's A, and here's the vector B. And let's say that we happen to know that there is some angle theta between them. In this case, it turns out that A dot B, in addition to being equal to A1, B1 plus A2, B2, et cetera, et cetera, et cetera, A dot B happens to be equal to the magnitude of A times the magnitude of B times the cosine of the angle between them. And this turns out to be very, very helpful because you can use dot products to find the angles between different vectors. This also gives us some interesting questions. For instance, what happens if we take the dot product of two vectors and we find that A dot B equals 0? Well, first of all, it could be the case that the magnitude of A or the magnitude of B are 0, but that's not particularly interesting. What's more common is when it happens to be the case that cosine theta is equal to 0. And you might recognize that cosine theta is equal to 0 when our angle is pi over 2 or 3 pi over 2. That is, when A and B are perpendicular. So in fact, it turns out to be a theorem that A and B are perpendicular if and only if, which is a very strong mathematical statement, A dot B equals 0. So this lets us check. The dot product gives us actually a very powerful tool. It allows us to check right away if two vectors are orthogonal to each other. If they're perpendicular, if they're orthogonal, the dot product is 0 right away. What does the dot product actually do for us? Well, what it does is it kind of measures their same directionness. How much are these two vectors in the same direction? And it's all about that cosine theta. If our two vectors happen to be more or less in the same direction at a somewhat acute angle, well, then that angle is small, and cosine theta is going to be positive. If our two vectors are perpendicular, well, then cosine theta is going to be 0. And if the two vectors are pointing in broadly opposite directions, past 90 degrees, then the dot product will be negative. And in fact, if they are perfectly diametrically opposed, if they are perfectly opposite each other, you'll get a very large negative dot product. One notable application of the dot product is to find components and projections of vectors. It's often useful in physics and math and other things to ask, let's say I've got this vector A and this vector B, is to kind of project vector B down and ask, well, what is the extent of vector B in the direction of vector A? And sometimes what we'll do is we'll use this particular notation. We will call this the component in the direction of A of vector B, the component or comp. The component of B in the direction of A. Now, for a lot of you, you probably recognize this from a previous class, and you can say to me, well, that's just going to be the magnitude of B times the cosine of the angle. Now, this might ring a little bell based on the dot product. You might say, well, that looks almost like the formula for a dot product. So but it's just missing the magnitude of A. So I could in fact write this as A dot B divided by the magnitude of A. This is actually not as arbitrary as it looks, especially if you consider that if you kind of take A and the magnitude of A and group them up here, and you say to yourself, well, this is really just the unit vector in the direction of A. This is A hat dot B. So remember that the dot product tells you how much two vectors are in the same direction. Well, now it's telling you how much is B in the direction of A. And we've made A a unit vector so as to take out all influence of the magnitude of A. We've just made this vector, we've just made this component purely based on the magnitude of B. Now, this is actually just a scalar number. This gives us the length of that arrow. Sometimes, though, we want the actual vector. What if we want the actual vector here? Well, we've got a length. This is a scalar. This is a dot product. So this actual vector goes by a different name. This is actually called the projection, or proj, onto A of B. And so if we want that actual vector, remember that a vector has two components. It has a magnitude and a direction. So we can actually just take a magnitude and multiply it by a direction. How big do we want that projection to be? Well, we want it to be equal to the component of B in that direction. That's how long it should be. It should have the same length. And the direction we want it to point in is we want it to point in the direction of A. So what we'll do is we'll take the unit vector in the direction of A. So we're just going to take a scalar, the length of that component of B, multiply it by the unit vector in the direction of A. And we get to this kind of peculiar set of formulas. So we get A dot B over the magnitude of A. There's the length of the component, times, I should really be careful with my dots. This is a times, not a dot product. A over its own magnitude. And so you'll often see this, and you'll see this written in your book this way. A dot B over the magnitude of A squared times the vector A. And it's worth noting that all of this is just a scalar that sizes that component, that vector projection, exactly right. So let's do a quick little example of this just to make sure that I'm not totally insane. So let's pick two seemingly random vectors. We're going to pick the vector 1, 1. We're going to do this in 2D, so it's a little bit easier to see. We'll pick the vector 1, 1. There's no need for an extra comma there. And we'll pick the vector negative 2, 3. Should be something like this. Now, they're not actually perpendicular, as we'll show in a second. So let's say I want to project 1, 1 onto 2, 3. So if I go ahead and find that component, if I go ahead and find the component, I need to take the dot product of these two vectors. So negative 2, 3 dot 1, 1, which should give me negative 2 plus 3 equals positive 1. So here's A dot B. If I then find that projection, that will be 1 divided by the magnitude of a, which happens to be root, let's see, 4 plus 9 is 13. It's a very small projection. 1 over root 13 is a little over a quarter, a little over 0.25. It's like 0.28 or something, which makes sense because we're going to get a pretty small projection off of b. And then if I actually wanted to find the component, the actual vector in that direction, I would do 1 over root 13, and I would multiply it by the unit vector in the direction of a, which will be negative 2 over root 13, comma 3 over root 13, which would give me finally the vector negative 2 over 13, 3 over 13, which is transparently parallel to a, and if you actually do the math, has exactly a magnitude 1 over root 13.